In the last lecture, we have seen how to find the value of the integral numerically. Okay, so in this lecture, we will try to solve the differential equation numerically. Okay, so we know the solution of differential equation exists if it satisfies the Lipschitz conditions, and then we are able to get the solution by the theorem, uniqueness and existence theorem. Okay, so now what are the methods to solve the given differential equation numerically? So particularly, we will think of the first order, first degree differential equation, or we call that as a ordinary differential equation. Okay, so let us try to understand the ordinary differential equation. Okay. I hope you are able to see this.
Yes, sir.
Okay, so we have to think of numerical solution, ordinary differential equation. Okay. And here particularly we will be solving first order differential equation. So what we require, suppose we have dy by dx is equal to f of xy being the given ordinary differential equation. Now we want to solve this ordinary differential equation. So here we should be provided with some initial conditions to solve this equation completely. Okay, otherwise we will get the general solution. But being an engineer, we are more interested in the values rather than the nature of the values. So for example, if somebody says that the solution is going to be some constant, okay, but what is the value of the constant? What is the nature of the constant? That's what we are interested more. Okay, so here again, if we want to solve this differential equation, we need to have the conditions. Okay, either they may be the initial condition or the boundary condition. So the problem with the initial condition is called initial value problem, and the problem with the boundary condition is called boundary value problem. So here particularly we will be solving the initial value problem. So with the initial conditions, okay, x0, y0. Okay, so what are these conditions? X0 and y0. That is, what is y0? Y0 is nothing but y at x0. Okay, so we have y at x0. Okay, so this is the first order differential equation. So we need this initial condition, and if this initial condition are satisfied, then the solution passing through this point, or in another word, the curve passing through this point and satisfying this differential equation is called the solution of the differential equation. So here we are trying to find the curve which satisfies this differential equation and which passes through the given initial value. Okay, so here we have to think of these are the initial values. So sometimes directly y at x0 is equal to, we need to understand the notation. So y at x0 is equal to given. So we should be able to understand what is going to be x0 and what is going to be y0. Okay, so here we have some basic methods. Okay, so like the first, we can use the Taylor series method to solve this, but the Taylor series method is a hybrid method which gives you analytic solution in the form of the power series, as well as if you put the value, it gives you the numerical solution also. And the important thing is that the Taylor series method is a single step method. So depending on the number of steps, we can say the single step methods and multi-step methods. So Taylor series method is a single step method. Then other method like Euler method is a multi-step method. Okay, So as we have seen the step size in the interpolation as well as in the numerical integration. Okay, so the notation for the step size remains same. So what we'll be having here, let H be the step size. Okay, H be the step size. Now, some methods are again, though they are multi-step methods, they correct the value. Okay, and they sometimes predict the value and correct the value. Okay, so these methods are called predictor corrector method. So here in this chapter, we'll see two types of methods. One is going to be a multi-step method and other is the predictor corrector method. So first of all, we'll try to understand what is the Euler method. Okay, so let us try to understand Euler method. So here, what we have the given differential equation, okay, and then with the given condition. So we have Euler method. Okay. So some people pronounce this as Euler also. Okay, actually it's Euler. Okay. So now, what is the Euler method? So what we have, let the given differential equation dy by dx equal to f of xy be the given ordinary differential equation with the initial conditions x0 and y0. Okay. Then, okay, so what we are doing here, we have the point x0, y0. Then we'll move to the next point x1, y1. Then we'll move to the next point x2, y2. And so on. We'll reach at the particular point where we want x and y. Okay, so these are actually the segments that we are approximating. Okay, so here we approximate the n plus 1th value of y using the previous value, that is yn, and here you are having h times f of x and y. Okay, so this is the formula for the Euler's method to solve the differential equation numerically. Okay, and here what we can have is where n is running from 0, 1 to 3 onwards. Okay, so if you put n is equal to 0, then we are able to calculate y1. If you put x is equal to 1, we are able to calculate y2 and so on. Okay, so is there any doubt in this formula or up to 8?
No, sir.
Okay, so all of you got this idea of a numerical solution and the Euler's method.
Yes, sir.
Okay, so I hope you are getting this right. Okay, let us try to solve one problem based on this Euler method. So we go with the example. What we'll be having, solve dy by dx is equal to x plus y with the condition y at 0 is equal to 1. Euler's method at x is equal to. Again, so that's what the problem is. So we have given a differential equation, we have given the initial values. Again, so we can go for the solution. Okay, so let us think of what is given to you. Dy by dx is equal to x plus y. With, now we need to understand y at 0 is equal to 1. So this is actually y0. and you can get x0 here. So this is the value of x0. So we got x0 is equal to 1. Okay. Now we have to find the value of y at
x0 will be 0, na?
Yes, x0 is going to be 0. Good. Okay. So x0 is going to be 0 and x is going to be 1. Right? And this is going to be the function. And what we have, f of xy is equal to x plus y. So this is all the given data. Okay. This is all going to be the given data. Now, what do we know? So by Euler's method, always write the formula. Okay. So what is the value which is not given? You can see the Euler formula here. So you know x0, you know y0. This is y0. What value you don't know is?
Step size.
Step size. Correct. Okay. So that step size is missing. So if I go with the Euler formula, then I need h. But before I go for the calculation, I have to find out h. Okay. So usually when we apply Euler method, okay, we go for 5 steps. How many steps we go for?
5 steps.
5 steps. Okay, so remember this. Okay, we go for 5 steps. Okay, and how the step size is calculated? The step size is calculated always x minus x0 by n, and this is going to be h. So previously we used to call this as xn. Okay, and here what will happen? H is equal to, so it is 1 minus 0, and number of steps we have decided 5. So is it 0.2? Is that okay? Are you okay this
Yes, sir.
calculation?
Yes, sir.
Yes. Okay. So, and what we have, hence we have h is equal to with h is equal to 0.2, because we go for the 5 steps. Okay, and how this step size is calculated using this. Okay.
So we can go with any number of steps, right? Like 10
No,
steps.
we can go for any number of steps. Okay, so if you take more number of steps, your answer will be more accurate. Okay, here again we are going with the approximation. Okay, if you take more number of steps, that means the step size will be smaller, and your step size is smaller, then your error will be less, your answer will be more accurate. Is that okay?
Yes.
But usually
Yes,
we
sir.
go with the 5 steps. Okay. For Euler method, we go with the 5 steps. Again, we'll see as the methods will come. I'll tell you for each method how we are going to have the number of steps. Okay. So here, what is the by Euler method? What we get? So we get yn plus 1 is equal to, always write the general formula. So yn plus h times f of xn. In when or where n is running from 0, 1, 2, 3. Okay. So consider what we have to consider, what we know. We know x0. X0 is going to be 0. We know h. H is going to be 0.2. And we know y0. Y0 is going to be 1. Is that okay? Are you getting this? So we have, what we will be having? Y1 is equal to y0 plus h times f of x0 y0. Is that okay? Are you getting this formula?
Yes, sir.
We put n is equal to 0 because available is x0 y0. Okay, so when we know x0 y0, we are able to calculate x1 y1. So as we have seen here, how this curve progresses. Okay, so here we are right now here, then we will move here, and then the next step, and so on. And finally, we will reach to our x and y, or x and y. Okay, so now we have this formula. So y1 is equal to y0 plus h times f of x0, y0. So y0 is going to be 1, h is going to be 0.2. And what is f here? So you can see f of xy is x plus y. So it will be here x0 is 0 and y0 is going to be 1. Okay, so you have to remember this, that the function value, okay, always changes. Okay, so we have to consider f. Okay, and now we can see. Okay, so what we get here, 1 plus this is going to be 0.2, and here we have this is 1. Okay, so what will be the value? Is that 1.2?
Yes, sir.
Yes, sir.
Yes, sir.
So this is 1.2. So what actually we got? We got here y at x1. So what is x1? Again, we know xi is equal to x0 plus I times h. So here x1 is going to be 0.2 and the value is going to be 1.2. So we got here the value of y1. So you can see here we have x0 is equal to 0 and we have to reach x is equal to 1. And now we have decided step size is going to be 0.2. Okay, so here we have x1 which is 0.2, then we have 0.4, this is x2, then we have 0.6, this is x3, then we have 0.8 and this is x4. So corresponding value y0 we know that is going to be 1, y1 we have to calculate, y2 we have to calculate, y3 we have to calculate, y4 we have to calculate, and finally we have to reach to y5. Okay, now one more thing that we need to understand, okay, is when we have y1 and y2, we are able to calculate the value of when we have y0 and x0, we are able to calculate the value of y1. When we have the value of x1 and y1, we are able to calculate y2. When we have x2 and y2, we are able to calculate y3. When we have x3 and y3, we are able to calculate y4. And when we have x4 and y4, we are able to calculate y5. Okay, so actually we have to use up to x4. Okay, so we have to use up to x4. So we got the value of y1 here again, and hence let us try to calculate the value of y2. Okay, so what we have here, hence we have x1 is equal to, now x1 is going to be 0.2, y1 is equal to 1.2, and h we know is going to be 0.2. So we get what will be having y2 is equal to, it will be y1 plus h times f of x1 y1. Okay, so we get here f of x1 y1. And now let us calculate. So it is 1.2 plus this is going to be 0.2 times. Here we have x1 is 0.2 and this is going to be 1.2. So you can calculate what this value is going to be. 1.2 plus this value is going to be 0.2 into 1.2. Okay, you can have this is 0.2 into 1.2. So with this value, what do you get for y2? This value you are getting for y2.
1.48.
1.48.
Yes, very good. So it is going to be 1.48. Good. Okay. So now what we have next step? So we have x. This is going to be x2. So x2 is going to be 0.4. How we are getting x2? x2 is going to be x1 plus h. Okay. So x2 is going to be 0.4. y2 is going to be 1.48. And we know that h is going to be 0.2 again. So we get, again, what we are able to get here. See, again, we have to write the formula for y3. So y3 is y2 plus h times f of x2 y2. So we get here, this is going to be 1.48 plus is going to be 0.2 times. Here we have x2, so it is going to be 0.4 and plus, so it is going to be 1.48. Why we are getting this statement? Because we know f of xy is equal to x plus y. Okay, so can you give me the value of y3?
So it's 1.856.
1.856.
1.856. Very good. Okay, so we got here the value of y3. Okay, and hence, what do you do next for the next step? Consider x3 is equal to, is it 0.6 and y3 is equal to 1.856. Okay, h is equal to 0.2. So we have, what we'll be having here, y4 is equal to y3 plus h times f of x3 y3. So what you can have here is going to be 1.856 plus we have 0.2 times. Here we get 0.6 plus we get 1.856. So we have here 1.856. Can you get me the value of y4?
2.3472.
5472.
3472.
2.
Okay, that's good. Okay, so you got a value. Okay, I hope you're enjoying this. You're finding this easy. Okay, that's good. Okay, so next step we have x4 is equal to 0.8 and y4 is equal to 0.3472 with h is equal to 0.8. So we get, now we have to find out y5. So y5 is equal to y4 plus h times f of x4 y4. So what do you get here? 2.3472 plus 0.2 times. This is going to be 0.8 plus here we have 2.3472. Okay, so can you get y5?
2.97664.
2.97664. Any more digit? Or that is sufficient? That's what you are getting all.
Yes.
Please check that you are all of you are calculating and then you are getting the same value. Okay, if there is any difference,
sir.
you need to tell me. Okay. So actually, what we have calculated is this is y at x5. We have calculated a y5. That means y at x5. So what is the value of x5? We can see we have marked here. Okay. So you can see what we want to calculate. What is our final answer? We want to calculate y5, you know?
Yes, it's
Yes, sir.
2.9816.
Okay, so that means we have calculated the value of y at x5, which means we have calculated y at 1, and that is going to be 2.97664. So we can say the value of y at x is equal to 1 is 2.97664. So this is our final answer. Okay, so this is going to be the final answer. Okay, so do you have any doubt in this example? Is there any doubt in this example, or is there any doubt up to 8?
No, sir.
Okay, all of you are getting this one?
Yes, sir.
Yes, sir.
Got this? So in Euler method, what we know is we know the answer values for the previous step. So we can use them and go for the next step. So that means if I know x0, y0, I can move on to x1, y1. If I know x1, y1, I can move on to x2, y2. If I know x2, y2, I can move on x3, y3, and like that. Most important thing that you need to understand is we never use the final value of x. Okay, so you can see in the calculation that we have not used x is equal to 1. but we have used x4 to calculate the value of y5. Okay, and if I use the value of x5, then that means I am calculating the next step. Okay, so that thing you need to understand. Okay, so as I said, for Euler method, we need to use 5 steps. Okay, we have to calculate our final answer in 5 steps. Okay, so if you reduce the step size, your accuracy will be more. Okay, and the accuracy expected from you is 10 raised to minus 4. Okay, so the accuracy expected from you is 10 raised to minus 4. That means you must write at least your answer correct up to 4 digits. Okay, 10 raised to minus 4 means the 4 places after the decimal point. So you must write your answer, or you must write at least 4 digits after the decimal point. So is there any doubt up to 8?
Sir, how to quickly check that we are getting the right answer?
Yes. Okay. So how we can check that we are getting the correct answer? You can solve this differential equation analytically and then find out the analytic solution. Okay. So once you get the analytic solution, then you can check whether you are following the correct or not. So for example, in this case, what we have, okay, see how you are able to get this good question. Okay. So here we are done with our this question, but I'll answer the query. Okay. So what is the question we have? Dy by dx is equal to x plus y. This is actually a very good equation. Okay, so I can write this as dy by dx. Then I'll be having minus y is equal to x. Can we write it like this?
Yes, you can use the integrating form.
Yes. So this is dy by dx plus py is equal to q, where p is a function of x and q is also the function of x. So this is the linear differential equation in y. And so here p is going to be minus 1, q is going to be x here. So the general solution is going to be y e raised to integration p dx is equal to integration e raised to integration p dx and into q and dx plus c. Okay, so when you solve this differential equation, you will get this constant c. Okay, so we, as I said, we are being an engineer, we are always interested in the values. Okay, so I want to know what is this constant, but I am interested in what is the value of the constant. Okay, and that's why we need to shift the numerical solution. Okay, so you now you have the analytic solution. So this can be solved analytically as it is a linear differential equation. Okay, so you can solve this and find out the analytic solution. Okay, here to find the value of this c, we have to use the given initial condition. So what we know is y0 is equal to 1 and x0 is equal to 0. So put x0 is equal to 0 and y0 is equal to 1 in the solution. So you can get the value of this c, and then after getting the value of c, you will get the complete solution. Now put the value of x is equal to 1 and see the value what you are getting for y. So you can compare these two and then see that your value is correct. Okay, so this is nothing but the verification of the method, whether your method is giving you the correct answer or not. Okay, so I hope I have answered your query.
Yes.
Okay, that's good. So is there any doubt up to 8?
No, sir.
Okay. So all of you got the problem, right? Okay. So you got the solution of this by using the Euler method. Okay. So let us try the another example. Okay. What we can have is, okay, find the value of y at x equal to 1.2. say 1.5 using Euler's method, satisfying dy by dx equal to x into x0 is equal to 1 and y is equal to. Okay. So this is the given problem. What we have, like dy by dx is equal to x into y. If x0 is equal to 1, y0 equal to 1, and x is equal to 1.5. So we have f of xy is equal to x into y. And what will be h? What will be the value of h?
0.1.
0.1.
Yes, good. So we have x0 is equal to 1 and x is going to be 1.5, and we want 5 steps. Okay, so we have 1.1, 1.2, 1.3, 1.4, and this will be 1.5. So y0 we know that's going to be 1. And hence, what we have to do is we have to consider these steps. Okay, what we have to do is we have to consider these steps. So we can get y1, we can get y2, we can get y3, y4, and y5. This is going to be x1, x2, x3, x4, and finally x5. Okay, so here h is going to be 9. Okay. Now let us calculate. So we have all the data which is required to solve the differential equation numerically. So we can say by Euler's method. Okay. We are having here yn plus 1 is equal to yn plus h times f of x and yn, where n is 0, 1, 2, 3 onwards. Okay, so we have what we have, x0 is equal to 1, y0 is equal to 1, and h is equal to 0.1. So we get, okay, what we are able to get here is y1 is equal to y0 plus h times f of x0 y0. So we get here y0 is 1, h is going to be 0.1. Now here, what is the function? X into y. So x is going to be 1 and y is going to be 1. So is that 1.1? Is that okay? Are you getting y1 is equal to 1.1? Are you getting this?
Yes, sir. Yes.
Yes. Okay. So now we have, okay, x1 is equal to 1.1, and we get here what we got, y1 is equal to 1.1 and h is equal to 0.1. So we have y2 is equal to y1 plus h times x f of x1 y1. That is going to be 1.1 plus 0.1 times, here we have 1.1 into 1.1. Okay, so what we get here, y2 is equal to, what is the value of y2 you are getting?
1.221.
1.221. Very good. Okay, so we got the value of y2. So consider x2 is equal to 1.2, y2 is equal to 1.221, and h is equal to 0.1. So we get what we are able to get here. So we can calculate y3. So it is going to be y2 plus h times f of x2 y2. Okay. So we got here, this is 1.221 plus we have, this is going to be 0.1, and here we have 1.2 into 1.221. Okay, so we got y3 is equal to
1.36752.
very good 1.36752. Okay, we have x3 is equal to 1.3, y3 is equal to 1.36752, and h is equal to 0.1. So what we can have now, we can go for y4. So y4 is y3 plus h times f of x3 y3. Okay, and this is 1.36752 plus we'll be having 0.1, and here we have 1.3, 1.36752. So that's what we got here. And now we are able to calculate the value of y4. So y4 is equal to this value of y4 you are getting
1.5453
1.54 by 3.
by 3.
Some more digits.
Sir, I have rounded off 3.
So actually it is 1.5452.
1.5452
98.
976.
98.
76.
There are more than one value, so we need to confirm.
So it is, I think, 976.
Okay, so is it okay? 0.54529. What is the next digit? Is it 7?
76, sir.
7, right?
Yes.
Yes, sir, and then 6.
Okay, so it is 97.
6.
Okay, see, we need at least 6 digits, so 4 will be correct. Okay, so that's why I recommend you to use 6 digits. Okay, so 5452 and 97, and hence we have y5 is equal to y4 plus h times f of x2 y2. Okay, so here we got 1.545297 plus we'll be having 0.1. This is 1.4 into 1.5452 and 97. We can have, and hence we can get the value of y5. So give me the value of y5. The value of y5 you are getting
1.761638.
okay. So please, others, please verify this value. So 1.7616.
Yes, sir. I'm getting the same value.
Okay, that's good. So we can say the value of y at x equal to 1.5 is 1.7616. Okay, so this is the final answer. So that's how we are able to use the Euler's method, okay, to get the value. Okay, so is there any doubt now in this question?
No,
Is there any
sir.
doubt? Are you getting this? Okay, so you got this right. I hope all of you are getting the same value, right?
Yes, sir.
Yes. Okay. Very good. Okay. So now we have solved the problems using Euler method. Okay. So actually, what we did recently is dy by dx is the velocity. Okay. So using the velocity, we will try to catch up the moving particle or the moving body. Okay. And by Euler method, we got how it is traveling. Okay. So at what time and where it will be there, where that body will be, or where the moving vehicle will be. But whatever the location we have got now, the value of y, x0, y0, that is the location we get. Okay. So how accurate is that? Okay. Can we make it more accurate? Okay. So here we have never thought of the accuracy in this method, or we have not considered what is the error in calculating this value of y. Okay. And hence we need to modify this method. Okay. So this method will not consider about the error, but we need more accurate answer, and that's why we have to consider the error and how to remove this error. Okay. So to remove this error, we need to understand the Euler's modified method, or some people write it as modified Euler method. Okay, so we go for the modified Euler method. So we can see what is the modification in the Euler method. So we have modified Euler's. And I have told you that there are some methods which are multi-step. So Euler method is going to be multi-step method, as well as this method is also going to be multi-step method. But this method is also predictor corrector method. This method is also a predictor corrector method. So that means it will give you the location, it will predict the location, and then again it will correct that location. So it will, as we zoom in, we go more and more accurate to the location. Okay, so this method is called as the predictor corrector method, which predicts the location and then corrects that location or make that location more accurate, okay, using the corrector formula. So here, yes, Jason.
So
Yeah.
when I solved the differential equation to check it, so I got 1.86824. So we're not getting correct answer.
Okay, this value you are not, you are getting different.
No, sir. Like when I solved a differential equation
Okay,
to get the correct answer,
okay.
I got 1.868. I didn't get
This
1.
differential equation you solved, right?
Yeah, sir.
Okay, so this differential equation you can solve by using the variable separable method. Okay, so I
Yeah,
hope
sir, I got-
you have used the variable separable method. Okay, so the value that you have got will be nearby this. These are the approximations. Got it?
Yes, I got that.
Yes.
I thought it'd be more accurate. That's it.
Yes. Okay, so now that's what I said. This method will not take care of the error. Okay, whatever the error in the calculation, this method will not take care. And that's why we have to go for Euler modified method so that we can get more accurate answer. Got it, Jason?
Yes.
Yes. So we have to go for the modification of this method. This method says that here somewhere it is lying. Okay, but accuracy is not guaranteed. Okay, so we have to guarantee more accuracy, and that's why we go with the modified Euler method. Okay, so what is modified Euler method is that we need to understand. Okay, so here we have the given things always as usual. So we have dy by dx is equal to the function of x and y, okay, with the initial conditions x0 and y0. Okay, so consider. Okay, now you can see the formula. Okay, y1 is equal to y0 plus h times f of x0 y0. What this formula is for? The Euler formula, Euler method formula, no?
Yes,
This
sir.
is the previous formula
sir.
that we have used. Okay, so this formula is called as predictor formula. This formula is called as predictor formula. So this formula will give you some location that nearby here it lies. Okay, and then we have to correct this. Okay, so and we have to correct this first value y1. This bracket you have to write it as I am writing. So please be careful for the notation. Okay, so here y1 and this one denotes the first correction. Okay, this denotes the first correction. Okay, so first correction to y1 is y0 plus h by 2. Okay, and here we have, this is going to be f of x0 y0 plus f of x1 y1. Okay, so see, it is using the current location also, and it is using the previous known location also. Okay, so that it will make the more correct answer, and this formula is called as corrector formula. This is the corrector formula. Okay, so that's why this Euler modified method, or the modified Euler method, is called the predictor corrector method. So it is called the predictor corrector method. So here we have to predict the value and then correct that value till we get the most accurate value. And once we get the most accurate value, then we move to the next step. Okay, so what is the difference between the previous method and this method? This method will not allow you to move onwards if your value is not correct. Okay, so it will correct the value up to the accuracy. After you get the accurate value, then you can move to the next step. In the previous method, there was no chance to make the answer more accurate. So we were just moving on. So we got the value of x1, y1, we move on to x2, y2. We got the value of x2, y2, we move on to x3, y3, and like that. But in modified Euler method, you will move to x1, y1, and then we will correct the value of y1. And once the correct value of y1 is obtained, then we move to the next step. Okay, so this is how the Euler's method is modified. So do you have any doubt in this now?
Sir,
Yes,
sir, in this, how many steps we are going to take?
2 steps. We are going to use 2 steps in Euler modified method. Yeah,
Okay,
because
sir.
it will not allow you to move the next step till you correct the value. Okay, so till you get the most accurate value, then only it will allow you to move to the next step. Okay, so is there any doubt in this formula? Where?
Excuse me, sir.
Yes, please.
Sir, why are you getting error in first method?
First method. Why do we are getting the error in the first method, right? Okay, so these are all the numerical methods. So these are all approximate values. Okay, so when we go with the approximation, we always have the error. Okay, and that's why it is called approximate. Okay, it is not the complete one. So as I have told you in the previous example, when you this was the LDE. Okay, when you solve the LDE and you get the correct answer by using the analytic solution. So basically, why these numerical methods are used? Because we are not able to solve the problems using the analytic methods. Okay, why do we use these methods? When we are not able to solve the problem by using analytic method. Okay, and that's why we use the numerical methods. Okay, so the examples that I have taken, purposely I have taken so that you can verify the answer, how accurate it is. Okay, so the first one linear, the second one variable separable. But actually these methods are used when the analytic solution sometimes does not exist. Okay, so we solve it numerically. Is there any other doubt?
Thank you, sir.
Welcome. So is there any other doubt? This one?
Yes, sir.
Okay.
So what is that y1 raised to 1 fractal?
I1, 1. That means it is the first correction. Okay, so it is going to be the first correction. Okay,
And sir,
so
how many corrections we are going to make?
we are going to make the corrections till we get the accurate value.
Okay.
Okay, so here I have, this is going to be first correction. What will be the second correction? So y1 and the second correction. So what do you have the second correction? Y0 plus h by 2. Here we have f of x0 y0 plus we'll be having f of x1 y1 1. Okay, so we use the previous value as well as the current value. Okay, so this was the first correction. Then using this first correction, I am making another correction. Okay, until we have to go on correcting this till we get the accurate answer. So as I have told you, the accuracy required is 10 raised to minus 4. So that means we have to match at least 4 digits. Okay, what we have to do is we have to match at least 4 digits. As we have done in the case of transcendental equation, we have solved the problems by using the Differential method and other methods also, and we used to match the previous value to the next value. So if at least 4 digits are matched, we can move on. Got it? I hope I answer your query, right?
Yes, sir. Got
Yes,
it.
sir. Thank you.
Okay, okay, that's great. Okay.